This video is about a mathematical problem that I've been obsessed with since I was a child. It's a simple counting game that you can play on your fingers. As a child, I came up with this game, and I solved the problem for 1 to 5 fingers. But I always wondered if you could generalize the solution to 6, 7, or even n fingers. I tried solving this problem as a child, and again in my undergraduate days, and again in my postgraduate days, and again in recent days, but the solution always eluded me. Now, I'd later learn that this problem already exists. It pops up in all sorts of places, on chessboards, on graphs, on toast racks, and a solution already exists. But that solution is really difficult to understand, and I never dedicated myself to getting my head around it. Until now. I recently committed myself to finally understanding this solution, and boy was it cathartic to finally resolve this childhood trauma is a bit of a strong word, but anyway, that's what I'll share with you today. And I know this is a really long video, but I didn't want to skip any details as I want you to have a full and complete understanding of this proof, as for me, mathematics is less about the final answer and more about the process. I'll let you know when there is a good moment to take a break, but please come back because this whole proof is amazing with lots of really insightful details. Come with me on this journey because while you've probably never thought about this problem before, it's a great problem with many fascinating steps in its intricate solution. So, what the heck is this problem? Well, let me take you back to my childhood and how I first conceived it. And this is honestly true. This is the sort of thing that went through my mind back then. As a child, I loved films. I still do. My dad had an enormous VHS collection and we used to love watching them together. VHS, kind of showing my age here. Back then, I loved Independence Day. The effect of the beam weapon as it destroyed all the buildings, I loved the spectacle. It was a simpler time, back when Will Smith punched the right things. Anyway, for some reason, I started to wonder about this. Imagine that we're the aliens and we want to blow up 5 buildings. We're going to blow them up one by one. We can start with any building, but here's the rule. Once we've blown up one building, we're not allowed to destroy one of its neighbors in the next step. So we can start anywhere. Let's say we start with building number 2. Now in the next step, we're not allowed to destroy one of 2's neighbors, so we can't destroy 1 or 3. So we have to destroy building 4 or building 5 next. Let's say that we destroy building 5. In the next step, we can't destroy one of 5's neighbors, we have to destroy building 1 or building 3 next. Note that if I destroy building number 1 next, then I am allowed to destroy building 3 after that. These aren't considered neighbors just because the building between them has been destroyed. So if I destroy 1 next, I can choose to destroy either 3 or 4. But notice, if I destroy building number 4 next, then I'm stuck, because whichever one I destroy next, I can't destroy its neighbor. So I have to destroy building number 3, as I can't destroy building 4 as it neighbors 5. So let's destroy building number 3. After this, I can't destroy building number 4 or building number 2, I have to destroy building number 1 next. And finally, we destroy building number 4. So, 25314 is a valid solution, but the problem is, how many solutions are there for 5 buildings? Or what if we had 6 buildings, or 7 buildings, or n buildings? The 3 case is impossible. If you start from the middle, then you can't proceed, and if you start from an edge, then you're in that 2 adjacent situation which we just saw wasn't possible. The 4 case is easy. If you start from an edge, then you're in the 3 case, which we just said was impossible, so we have to start with one of the centrals. Once you've picked one of the centrals, the rest of the moves are predetermined, so there are exactly 2 solutions. The 5 case is the one that I loved as a child. I used to do it on my hand, imagining that each building was one of my 5 digits, and then seeing if I could press them down in such a way that I never pressed down 2 neighboring digits successively. Pause the video now if you want to work out how many solutions there are for the 5 case. As a child, I managed to work out that there are 12. And then I realized it's actually 14 because for some reason it took me a while to notice this one and its mirror image. And to this very day, I still cycle through all 14 of them on my hand as a fidgeting habit. So far we have that the 3 case has 0 solutions, the 4 case has 2, the 5 case has 14. For completeness we can go backwards and say the 2 case clearly has 0 solutions and the 1 case has 1 solution. Now there isn't an obvious pattern here, so what do we think for the 6 case? Now, I gave up on this as a child because I needed to use an extra hand, and who has time for that? As a teen, I'd learnt about basic sequences, so I painstakingly computed, by hand, literally, the number of solutions for the 6 case, and it turns out that there are 90. But none of the techniques I knew at the time worked when analysing this sequence, as it isn't a linear, quadratic, cubic, or a Fibonacci sequence. As an undergrad, I felt myself more equipped to tackle this problem. I had much more mathematical machinery in my arsenal at the time. Something about the problem felt a bit proof by induction-y, like the 6 case is just the 5 case but with an extra finger. So if you start with this finger, then you just have the 5 case again, minus the cases which start with the thumb. Sounds good in principle, but it doesn't really work. I eventually abandoned this idea because if you start with this finger, for example, you've broken it into a 3 case and a 2 case which interact in weird ways, and there's just far too many cases to consider. I also knew about graph theory. Let each vertex represent a finger, then draw an edge between 2 vertices if they represent fingers which are not neighbouring. I would later learn that these graphs are called the path complement graphs on n vertices. Now the problem basically became how many ways are there of traversing each graph such that you start and finish at different vertices and you visit every vertex exactly once. In other words, how many Hamiltonian paths exist for each graph. But that, it turns out, is probably a much more difficult problem, as there is no general way to compute the number of Hamiltonian paths on an arbitrary graph. During my PhD, I took another crack at it, simplifying things and representing each solution as a string of numbers such that no 2 adjacent numbers had a difference of exactly 1. I knew that there must be some combinatorial argument that would generalize up to n fingers. Now, at that time, I was a much more experienced mathematician, so I did what every good mathematician does and checked to see if anyone else had solved the problem. The only difficulty I had was it's hard to find reference to a problem if you don't already know its name. Maybe I was the first to even think about this problem. But no, it's extremely rare to be the first, even if you do think about it in a new context. And I did eventually find something in the fantastic online encyclopedia of integer sequences. I typed in those numbers that have haunted me ever since my teenage years. 2, 14, 90. Lo and behold, the first results reference something called Hertzsprung's problem. Now, my first thought was, why on earth did Ejnar Hertzsprung, the guy most famous for stellar classification and the Hertzsprung-Russell diagram, care about such a weird counting problem? But, as it turns out, this is a different Hertzsprung. My second thought was then, wow, I really didn't expect Hertzsprung to be such a common name. But as it turns out, this Hertzsprung, Severin Hertzsprung, was Ejnar Hertzsprung's father, so it all made sense. Now, Severin trained as an astronomer and had a passion for mathematics, and he instilled that passion in his son, Ejnar. But Severin later worked in the financial sector, having abandoned academia, but remained a keen chess player. And that makes sense because there is a link to chess in this problem. You've probably heard of the n queens problem. The queen in chess can move vertically, horizontally, and diagonally any number of spaces. So the n queens problem is to place n queens on an n by n chessboard such that no queen can immediately capture another queen. Now, the king in chess can move in the same directions as the queen, but only one space at a time. So now consider the n kings problem, placing n kings on an n by n chessboard such that no king can immediately capture another. Add the additional constraint that we only want one king per row and per column, and hey, this is identical to my finger problem. Each row of the board represents a decision in the game, and placing a king means it blocks out you putting a king immediately before or after in the next row. So there is a one-to-one correspondence between the solutions to the finger game and the king game. This might be how Severin Hertzsprung first conceived the problem. He writes about it in a letter in 1887, where he describes the problem as listing integers such that no 2 adjacent integers have a difference of exactly 1, and then goes on to describe the chess way of visualizing the problem. He says it's n kings, but also adds an additional note that it's actually the n piece problem, where each piece is a combination of a rook and a king, since the rook can move horizontally and vertically any number of spaces, and that's where our only one piece per row and column condition arises. And though this letter is written in Danish, which I cannot read, I'm instantly drawn to those numbers. 2, 14, 90. They've been in my head for over a decade, and it still feels weird to know that so many others have considered this puzzle. So it became known as Hertzsprung's problem, and later Irving Kaplansky, who first published a solution to the problem in 1944, referred to it as the N-Kings problem, but also adds a similar footnote to say that this is really the N-piece problem, where the piece in question is really a rook-king combination. He also brutally puts this problem down by referring to it as a first cousin, a mere shabby relative of the N-Queens problem. Though this is really a self-burn, as he admits he has failed to solve the N-Queens problem. So, we have a combinatorial approach based around permutations of the integers from 1 to n, a Hamiltonian graph problem, a chess problem, and also a toast problem? This might be my favourite comment that I've ever read in the OAIS. This sequence is also the solution to the toast problem, devised by my housemates and me as maths undergraduates some 27 years ago. Given a toast rack with n slots, how many ways can the slices be removed so that no two consecutive slices are removed from adjacent slots? David Jones, if you ever read this, you're a hero, and it warms my heart to know that there are maths undergraduates out there who have the same bizarre thoughts that I did after watching Independence Day. But anyway, that's the problem. Have a play around with it and see if you can come up with any ideas for what might be a good approach, but come straight back because we're about to get into the solution. But strap in, it's a doozy. We're going to need lots of little bits and pieces for this, so let me give you an overview of how the proof is going to work so that you can see where those bits and pieces are going to slot in. I'm also going to assume very little prior knowledge because the beauty of this proof is that it's very elementary. So apologies if I go over something that you already know. Don't worry about it, just enjoy the recap. Consider the for case for now, but when we do the proof for real, we'll consider the n case. How many ways are there of listing the integers from 1 to 4? Well, that's 4 factorial, 4 times 3 times 2 times 1, as there are 4 choices for the first number, 3 choices for the second, 2 choices for the third, and 1 choice left at the end. In this case, 4 factorial equals 24, so there are 24 different ways of listing them, and each listing is called a permutation. In general, if you have the first n integers, there are n factorial permutations. Think of each permutation as a set of instructions for how to play the finger game. So 4, 2, 3, 1 is saying finger 4, finger 2, finger 3, finger 1. This isn't a valid solution because I put down finger 2 followed by 3, which is illegal in the rules of the game. So here's what we want to do. We want to find how many of these permutations contain what I'm going to call a forbidden pair. A forbidden pair is a pair of successive entries in the permutation which have a difference of exactly 1. So 2 numbers that are next to each other and consecutive in either order. They're forbidden because they represent putting down 1 finger and then an adjacent finger on the next step, which breaks the rule of the game. And it doesn't matter which order we do it, like 3 followed by 2, they are neighbouring fingers going down one after another, which breaks the game. So here's what we want to do. We want to find how many permutations contain any amount of forbidden pairs. It doesn't matter how many forbidden pairs you contain, if you contain at least 1, you break the game. So if we find how many permutations contain any number of forbidden pairs, we delete them from our original n factorial permutations, and we will be left with the permutations with no forbidden pairs, and they are exactly the solutions we require. Now, there are some immediate problems that make this difficult. And the first problem is this: how many ways are there of containing a forbidden pair? For example, in the 4 case, we could have a forbidden pair at the start, like in 2, 3, 1, 4. We could have a forbidden pair in the middle, like in 1, 3, 2, 4. Or we could have a forbidden pair at the end, like in 1, 4, 2, 3. But that's not all, because we could have a forbidden pair at the start and at the end, like in 2, 1, 4, 3. We could even have one at the start and in the middle, like in 3, 2, 1, 4. There are 2 distinct forbidden pairs here, they've just been smushed together. And similarly over here, where we have a forbidden pair in the middle and at the end, like 4, 1, 2, 3. And that's still not all, because a permutation could contain a forbidden pair in all 3 positions, at the start, in the middle, and at the end, like in 1, 2, 3, 4. Remember, that's 3 distinct forbidden pairs, but they've all been smushed together. So how on earth are we going to count all of these possibilities? And remember, we want to do this in general. The 5 case is already wildly more complicated than the 4 case, never mind the n case. The next problem is that even enumerating the number of permutations in a specific case is far from easy. So for example, let's go back to the 4 case. There are 24 permutations in total, there are 6 options for what the forbidden pair has to be, and there are 3 different locations where we can find a forbidden pair. So we could say, okay, let's assume the forbidden pair is at the start. So there are 6 options for what that forbidden pair could be. Now once we've got a forbidden pair, we've already used up 2 of the numbers. So now there are 2 options left for what the third number could be. And then that leaves us 1 option left at the end. So there are 6 times 2 times 1 permutations equals 12, which have a forbidden pair at the start. And now we play the same game for the middle, where we say, okay, if the forbidden pair is in the middle, let's choose that forbidden pair first. There are 6 options for that, and then there are 2 options for what this first number could be, and then 1 option for the number at the end. So again, 6 times 2 times 1 gives us 12 permutations for the forbidden pair in the middle. And the exact same process for if the forbidden pair is at the end. So we have 12 plus 12 plus 12 equals 36 permutations, which contain 1 forbidden pair. Except that can't be right, because there are only 24 permutations in total. So this can't be right. And it isn't, because we've overcounted. To see why, consider a permutation like 1, 2, 3, 4. This has a forbidden pair at the start, so it got counted here. It also has a forbidden pair in the middle, so it got counted here, and it has a forbidden pair at the end, so it got counted here. So we've effectively counted it 3 times, which inflates this number beyond the actual answer. So this should give you a flavour of why this is a non-trivial problem. But in solving both of these, we'll solve the final problem, which is to count all permutations containing any number of forbidden pairs. This is where our extra bits and pieces come in, because there are some laws and results that will help us resolve these issues. The first thing we need is a way of enumerating all of the locations of a forbidden pair, and we'll solve that using something called the stars and bars. And the second thing we'll need is a clever way of enumerating the number of permutations that contain a specific amount of forbidden pairs. We'll do that with something called the Inclusion-Exclusion Principle. That's going to make sure we don't under or overcount the number of permutations in a specific case. And the last fact we'll need is just a little fact about Pascal's triangle, but that's only a little thing. Don't worry, we'll get to it. So that's the plan. And I know it seems like a lot, but don't worry, these little results here are quite small and easy to understand results, but they are really important because they're going to feed in to the main proof later. So let's get into it. Just a very, very brief aside for some basic combinatorics, because I used this heavily in my countdown video, but received a lot of comments from those unfamiliar with the concepts. Let's say I have n numbered cards, then we've seen that the number of ways of ordering them is n factorial, because there's n choices for the first, n minus 1 choices for the second, and so on down to the end where there's 1 choice, so n factorial ways of arranging them, and they are called the permutations on n. Now consider this. I've got a deck of n cards, and I want to take k of them into my hand, where the order of the cards in my hand doesn't matter. Just like in most card games, this would be considered the same hand as this. The order doesn't matter. How many ways are there of doing that? Well, the naive approach is to say, well, I have n choices for my first card, and then I have n minus 1 choices for my second card, times all the way down to n minus k plus 1 choices for my kth card. So a formula for this might be n times n minus 1 times all the way down to n minus k plus 1. And I'm going to do something a little bit strange here, but you'll see why in a second. I'm going to treat this like a fraction, so it's over 1 at the moment. I'm going to multiply numerator and denominator by n minus k times all the way down to 1. Since I've multiplied numerator and denominator by the same thing, the answer is still the same. But now I can rewrite this. At the top here, this is just n factorial, and at the bottom, that's just n minus k factorial. So let's rewrite it. Now this formula is actually incorrect, as it actually overcounts the number of hands. To see why, let's take k equals 3, so I want a hand of 3 cards, and consider this. The hand that I get by choosing first card 1, then card 2, then card 3, is the exact same hand as if I choose card 2, then card 1, then card 3, as the order of the hand doesn't matter. So this hand has been counted more than once, even though it's the same hand. How do we compensate for that? Well, every hand can be ordered in 3 factorial ways, or in general in k factorial ways. So every hand will be counted k factorial times. So this number here will be k factorial times too many. So the way we get the answer is to divide this by k factorial, and we get a very familiar formula. Simplifying, we get this formula, which is now the correct way to do it. We usually write it in shorthand like this, and pronounce it n choose k. It is the number of ways of given n objects, choose k of them. Other notations are used like NCK, which I used in my countdown video. The C stands for combination, because these are combinations where the order doesn't matter, as opposed to a permutation where every ordering is considered distinct. So, with that out of the way, let's look at the stars and bars. This is a classic combinatorics problem with a powerful recontextualization which helps us to solve it. The problem is this. Imagine you've got n identical balls and you want to assign them into k labeled bins, such that no bin is empty. So for example, let's take k equals 3, so I've got 3 bins here, and we'll take n equals 5. How many ways are there of distributing the 5 balls into the 3 bins such that no bin is empty? So this would be one valid way of doing it. This would be another valid way of doing it, which is considered distinct because the bins are labeled. But for example, this is considered the same solution because the balls are not labeled. They're all identical. This is not considered a valid solution because now I have an empty bin. How many ways are there of doing it? Well, if you play around with this case, you'll realize that there are 6 ways. But how many ways are there of doing it in generality? So to solve this, instead of assigning the balls to the bins, let's start with a row of 5 balls and assign the bins to the balls. What I'm going to do is I'm going to place a partition down. Now everything to the left of that partition will be considered bin 1. Now I'm going to place another partition down, and everything between the 2 partitions will be considered bin 2. And now whatever remains will be bin 3. So an identical problem to assign 5 balls to 3 bins is assign 2 partitions to a row of 5 balls. And how do we do that? Well, there are 4 potential positions for my partitions, as I'm not allowed to place them on the end, as that would correspond to an empty bin. Same over here, I can't have bin 3 being empty. So there are 4 positions, and I need to put the 2 partitions in a different place. If I put them together, then that would leave bin 2 empty. So there are 4 valid positions, and I need to select 2 of them. So there are 4 choose 2 ways of putting down the partitions. And you will note that 4 choose 2 is 1, 2, 3, 4, 5, 6, the solution that we had before. Now let's look at how to do that in the general case. So let's imagine a row of n, not balls, but stars. And now I want to assign these to k bins, so I need to place down k-1 partitions, or bars. And how many ways are there of doing it? Well, after every star, there is a valid position for one of our bars. So there are n valid positions for the bars, except I'm not allowed to put one on the end, so there are in fact n-1 valid positions. So in other words, there are n-1 valid positions, and I want to select k-1 of them to place my bars. So there are n-1 objects, and I need to choose k-1 of them. This is n-1, choose k-1. And you will note that in my n equals 5, k equals 3 example, I get 4 choose 2, exactly the solution we had before. Stars and bars is a great reframing of the problem that's used in counting arguments across the whole world of combinatorics. We'll meet it again very soon in our solution to Hertzsprung's problem, but first, we need to look at the Inclusion-Exclusion Principle. So this is a principle which helps us count the sizes of sets, and I'm going to explain it with this sweet example. Literally, it's about ice cream. So imagine you work in a restaurant and you serve a dessert which can be accompanied with any choice of vanilla, chocolate, or strawberry ice cream. All combinations are acceptable. No, I don't have any brown chalk, so unfortunately we've got blue chocolate. And I don't know why I made the cake yellow, now it looks like a wedge of cheese, but just use your imagination. So all combinations of the 3 flavors are available, including having your dessert served with no ice cream. Now imagine this scenario. The obsessive but mathematically inept manager wants to know how many desserts there currently are with no ice cream, but all they know is the information for all of the other categories. So let's take this example. They tell you that there are 47 desserts out at the tables at the moment. So they want to know how many of the 47 desserts have no ice cream. But they do know this: the number of desserts with vanilla is 21, with chocolate it's 15, strawberry is 17, vanilla and chocolate 6, vanilla and strawberry 7, chocolate and strawberry 5, and with all 3 flavors is 2. And by the way, I'm probably one of those 2 people. And there's a subtlety here that we really need to be careful about. There are 21 desserts containing vanilla. That counts all desserts which contain some vanilla. So among that 21 are the desserts that contain just vanilla, the 6 desserts that contain vanilla and chocolate, the 7 desserts that contain vanilla and strawberry, and the 2 desserts that contain all 3 flavors. Similarly, there are 6 desserts containing vanilla and chocolate. That includes the desserts that contain just vanilla and chocolate, and the other options which contain both vanilla and chocolate. So these 2 are part of that 6. So how on earth are we going to untangle all of this in order to get the number of desserts with no ice cream? Well, we could start by adding the vanillas to the chocolates to the strawberries, and this gives us 53. Already, we can see that we've overcounted because there are only 47 desserts in total. But let's look at how we've overcounted. This Venn diagram shows all possibilities. If we add up the numbers in every region, including the number on the outside, which counts the number of desserts containing no ice cream, it must equal 47. But what have we done? Well, in adding the vanilla plus chocolate plus strawberry together, here's what we did. We added these 4 regions together when we included the vanillas, then we added these 4 regions together when we included all the chocolates, and then we added these 4 regions together when we included all the strawberries. So what we can see is that some regions have been counted twice, and the 3-way intersection has been counted thrice. What we actually want to do is we want to count all of these regions exactly once, because that will give us the number of ways that the desserts contain some ice cream. After that, we can subtract it from 47 and we'll get the number out here. So what can we do next? Well, what we can do is we can subtract all of the 2-way intersections. So we subtract 6, we subtract 7, we subtract 5, and that brings our total down to 35. But let's look at the Venn diagram to see what we've actually done. So when we subtracted vanilla and chocolate, we subtracted 1 from this region here, this 2-way intersection. Then when we subtracted vanilla and strawberry, we subtracted 1 from this 2-way intersection. And then finally, we subtracted chocolate strawberry, we delete 1 from this 2-way intersection here. And now notice that we've counted everything once, but we haven't counted the 3-way intersection at all. So now we can add that back in. So we add 2, bringing our total to 37. So we can see that there are exactly 37 desserts which contain some ice cream. 47 subtract 37, this number out here must be 10. And that's the answer. Now there are simpler ways of doing this exact problem where there are only 3 sets. But the advantage of this method is that it generalizes to any number of sets. So if I had more flavors of ice cream, and the problem was the same, I wanted to work out the number out here, then what I would do is I would include all of the single flavors, and then I would exclude the 2-way intersections, include the 3-way intersections, exclude the 4-way, include the 5-way, and so on, following that alternating pattern. And this should sound familiar, because what that does is it tells us the number of ways of containing any number of ice cream, thereby telling us the number of ways of containing no ice cream. Replace ice cream with forbidden pear, and you should see this starting to come together. Remember, we want the permutations containing no forbidden pairs. So if we find the permutations with at least one forbidden pair and include them, exclude the permutations with 2 forbidden pairs, re-include the permutation with 3 forbidden pairs, and so on, that will tell us the number of permutations containing any number of forbidden pairs, which then tells us the number of permutations containing no forbidden pairs, which is exactly what we're after. So that's it for the inclusion-exclusion principle. The last thing that we need to talk about is just a little bit of information about Pascal's triangle that you might have seen before, but I want to include it for completeness. It'll take about a minute, I promise. So you've probably seen Pascal's triangle before, and if you haven't, what are you doing? And the way we construct it is each row is formed from the sum of the 2 entries above it. So for example, 1 plus 3 equals 4, 3 plus 3 equals 6, and so on. We consider any entry outside this main triangle to be 0. So I'm just going to put like an invisible 0 here, just so that you can see what I mean. And that means that the rule of adding the 2 entries above it is consistent. So imagine that there's just a sea of zeros everywhere outside of this triangle. Now what you might not know is that you can use the choose function, n choose k, that we had before in order to output the rows of Pascal's triangle. So for example, this third row here is actually made of 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And this might look like the 4th row, but remember we start counting from 0. So we have the 0th row, the 1st row, the 2nd row, and so on. And on a specific row, we start with the 0th entry, 3 choose 0, the 1st, 2nd, and 3rd entry, 3 choose 3. Now there's just a few weird properties that we need to go through. So 3 choose 0 is 1, and in fact anything choose 0 is 1. And why is that? Because that means you take 3 objects and you want to choose 0 of them. Well, there's only one way to do it. You choose none of them. And also, what about a number like this? If I have something like 3 choose 4. Well, that means we have 3 objects and I want to select 4 of them. But that's impossible. There are no ways of doing it. So we say that whenever k is greater than n in n choose k, then we get 0. And again, that kind of generalizes to Pascal's triangle, because remember, we said that there's like an invisible 0 out here, which is where 3 choose 4 would go. And the final fact we need, which isn't entirely obvious, and that is that the alternating sum of any row equals 0. So for example, if I take 1, subtract 3, plus 3, subtract 1, it always equals 0. And it doesn't matter which row we choose, we always get 0. And why is that? Well, I'm not going to go into a formal proof right now because I don't want to take up much more time with all of this setup, but I'll show you my favorite sort of demonstration of why this is the case. Think about a row with an even number of entries. This is clearly 0 because of symmetry. And now look at the row after that. This number here, this 3 for example, it doesn't really matter what it is, but we get 3 going this way and 3 going that way. So its contribution to the next row is 6. However, on this side it's subtracted, and on this side it is added. So we get minus 3 on that side and plus 3 on that side, so its total contribution to the alternating sum is 0. And that's true for all of the entries on this even row. So that means that they contribute nothing to the odd row, and therefore the odd row will have alternating sum 0. So if every even row and every odd row have alternating sum 0, then that means every row has alternating sum 0. Not a formal proof, but just a demonstration to give you some intuition as to why this is the case. You can prove it formally using induction or the binomial theorem. Really easy to do, but I don't want to get into it right now. And I don't want to get into it right now because that is the final fact we need, the fact that the alternating sum on any row of Pascal's triangle is equal to 0. We finally have everything we need to tackle Hertzsprung's problem. Let's do it. And like I said before, this would be a nice time to take a quick break, but please come straight back because we're about to get into the thick of it, and it's amazing. Deep breath and... First, we start by enumerating the number of ways of forming a permutation with a forbidden pair. Now, we're going to prove this result in generality, but because there are so many variables floating around, lots of n's, lots of k's, lots of r's, it's good to keep a concrete case in mind. So many of my diagrams will be of the 6th case, but we will prove the result in general. So let n be the case that we're in, so for example n equals 6 means we're in the 6-finger game, and let k be the number of forbidden pairs that a permutation contains. How many possible ways are there of containing k forbidden pairs? That's the question, and to build your intuition, let's just look at a few cases of k. So for example, when k equals 1, that means I want to find the permutations that contain 1 forbidden pair. Now, I'm going to use diagrams like this to represent which numbers are present in the forbidden pair. So for example, a bar across 1, 2 represents that the permutation contains the forbidden pair 1, 2 somewhere. For example, 5, 1, 2, 6, 3, 4 contains an example of this case. And I want to be really clear here, this is different from the kind of diagram I had earlier. Earlier, a bar there represented the location of the forbidden pair, so at the start. This diagram represents which numbers we are selecting for the forbidden pair, and that forbidden pair can be anywhere in the permutation. Also note that we're going to be assuming for now that every forbidden pair is in ascending order. So a bar in this position represents the forbidden pair 1, 2. It doesn't represent 2, 1. We'll worry about the descending order cases a little bit later. Also note that this permutation here contains another forbidden pair. It contains 3, 4. But don't bother about that. We'll worry about that later when we do our inclusion-exclusion routine. To be precise, because these permutations will contain at least 1 forbidden pair, what k really means is we're going to be counting the number of permutations that contain at least k forbidden pairs. Stick with me. So when k equals 1, where we're counting the number of possible ways of containing at least 1 forbidden pair, we see that there are 5 possibilities. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. So 5 in this case. Let's look at k equals 2 because here's where things start getting complicated. Here we could have situations like this, where the 2 forbidden pairs are smushed together. So this represents a permutation which contains the forbidden pair 1, 2 and 2, 3, an example of which is 4, 5, 1, 2, 3, 6. Because there is only 1, 2, if you have the forbidden pair 1, 2, then the forbidden pair 2, 3 has to come immediately after and it's smushed together. So there are 4 possibilities for the smushed case. But also for k equals 2, we could have that the forbidden pairs are separate, like in 3, 4, 6, 1, 2, 5. So we have 6 possibilities for when our forbidden pairs are independent, bringing our total for k equals 2 to 10. Now, if you're a fan of Pascal's triangle, and let's be honest, if you're not a fan of Pascal's triangle, what are you doing? Given that this is a counting problem, you might have predicted that the next case is going to have a total of 10. Let's see. So for k equals 3, we could have that all 3 forbidden pairs are smushed together in a triple smushing, like in 5, 1, 2, 3, 4, 6, and there are 3 possibilities for that. Or we could have 2 smushed together and 1 single, like in 4, 5, 1, 2, 3, 6, and there are 6 possibilities for that. Or we could have that all 3 forbidden pairs are independent, like in 5, 6, 3, 4, 1, 2, and there is 1 possibility for that, which does indeed bring our total to 10. And you might have already figured out why Pascal's triangle is rearing its beautiful head. And that's because if I have n numbers in a row, and each dash is 2 numbers long, then there are essentially n-1 positions where I can place my dash. So 5 options in the 6th case, but n-1 in general. Now in each case, since I want to place down k of the dashes, and there are n-1 places to put it, there are n-1 choose k ways of placing a dash. So n-1 choose 1, n-1 choose 2, n-1 choose 3, and so on, and that's going to print out a row of Pascal's triangle. Now this is a perfectly acceptable way of counting the number of possibilities. In fact, this is how PhD era Alex did it, but then he ran into trouble. Remember when I told you not to worry about the descending order forbidden pairs? Well, this is where we need to start worrying about it. The k equals 1 case is fairly straightforward because we can just say, okay, each of these forbidden pairs can either appear ordered or reversed. So this dash here, for example, actually represents 2 options, the forbidden pair 1, 2, or the forbidden pair 2, 1, and this one represents 2, 3, or 3, 2, and so on, so we can just double the number of possibilities to get the true number of possibilities for k equals 1. Now the k equals 2 case is where things get weird. Focus on these 6 possibilities first, where the forbidden pairs appear independent and not smushed together. So there are actually 2 options for this forbidden pair, ordered or reversed, and there are 2 options for this forbidden pair, ordered or reversed. So there are 2 times 2 options for this possibility, because we can either have ordered ordered, ordered reversed, reversed ordered, or reversed reversed. So actually we need to times this 6 by 4 because each of the 6 possibilities has 4 options. I'm not going to write it as times 4 though, I'm going to write it as times 2 squared, because it's 2 choices times 2 choices, and thinking about it that way will help us to generalize. Now let's look at the smushed case. What happens if you reverse one of them? Well, this top one, for example, represents the forbidden pair 1, 2, and then 2, 3. But because there is only 1, 2, they have to come smushed together. What happens when you reverse one? Well, if you reverse 1, 2, then you get 2, 1. And now that doesn't smush together with 2, 3. So what we have to do is also reverse 2, 3 into 3, 2 and stick it on the other side so we get 3, 2, 1. In other words, the only other option is to reverse the entire thing. So actually, each of these possibilities only represents 2 distinct options. So like in the first case, we just need to times this 4 by 2. So that brings us to 32 total possibilities for the k equals 2 case. And this is where PhD era Alex gave up. It just feels like there are far too many different cases here. How on earth are we going to generalize this to an arbitrary amount of numbers and an arbitrary number of forbidden pairs? But there is a way, and the key is to spot that what is important in each possibility is how many parts there are. A part is a contiguous string of forbiddenness. So for example, up here, all of these options are formed from one part. All of these options are formed of one part. Yes, it's 2 forbidden pairs, but they've been smushed together into one contiguous string. Whereas, for k equals 2, these options are formed of 2 parts. It's 1, 2, which is independent from 3, 4, so 2 parts. Down here as well, these options are also formed of 2 parts. One part that's been bunched and one part that's out on its own, so 2 parts. Now the key insight is not to think of whether each forbidden pair is ordered or reversed, but whether each part appears ordered or reversed. Because it doesn't matter how long each part is, it can either be ordered or reversed. So one part, each part counts for 2 possibilities, ordered or reversed. One part, each option counts for 2 possibilities, ordered or reversed. 2 parts, then each part can appear ordered or reversed. So that's why we times by 2 squared. What do you think we're going to do when we have 3 parts? Well, let's do it. All of these appear in one part, so it can either be ordered or reversed. So each of these possibilities has 2 options. Each of these are formed of 2 parts, each of which can be ordered or reversed, so we need to times by 2 squared. And this possibility down here is formed of 3 parts, ordered or reversed, ordered or reversed, ordered or reversed, 2 times 2 times 2, so we need to times by 2 to the power of 3. So we have 38 total possibilities for the k equals 3 case. And I've just completed the diagram here by labeling each family of possibilities by how many parts they contain, because that tells us the power of 2 that we need to multiply the number of possibilities by. I've even added these 1s here. I know that 2 to the power of 1 equals 2, but that makes it consistent with the rest of the options. One part we multiply by 2 to the power of 1. And in general, if the forbidden pairs are distributed into r parts, we're going to multiply the number of possibilities by 2 to the power of r. Now the question becomes, for a given k, how many of the possibilities are split into 1 part, how many of them are split into 2 parts, into 3 parts, 4 parts, and so on? Because that really isn't obvious. Earlier, we said that the total number of possibilities was n minus 1 choose k. And that's fine, but if we want to use this idea, that to take into account whether they are ordered or reversed, we need to multiply each possibility by 2 to the power of the number of parts. We need to count them according to how many parts they have. And that's what we'll do next. So we're going to have n, the amount of numbers containing at least k forbidden pairs, but broken into r parts. So, we want to count the number of possibilities for a permutation on n distinct integers to contain k forbidden pairs, but split into r parts. Again, it's all getting confusing, so let's keep a very concrete example in mind. We'll stick with n equals 6, we'll set k equal to 3, so it will contain 3 forbidden pairs, and we'll split them into 2 parts, so r equals 2. An example might be something like this. So that's 3 distinct forbidden pairs, but separated into r parts. Here's another one. Again, 3 pairs into 2 parts. Now, on this left-hand side, we're going to deal with this specific case, n is 6, k is 3, r is 2. On that side, we'll build a general formula. So by looking at a concrete case, it's going to help us in deriving something more general. So we've got 2 examples of the sort of structure that we're looking for, but how do we count all of them? And how do we do it in general? Think about it this way. Between each of our n numbers is a slot. In our example, we're going to have 5 slots, which means in general, we'll have n minus 1 slots. Now I'm going to fill each of these slots with either a dash or a cross. A dash we've already seen, that's this thing up here. That represents that I'm choosing those 2 numbers for a forbidden pair. And a cross just means I'm not placing a dash there. So I'm going to put the crosses up here so you can see what I mean. Since I want 3 forbidden pairs, that means I want 3 dashes, or in general, k dashes. Since I'm filling the rest of the slots up with crosses, that means I necessarily have to place down 2 crosses. Or in general, the number of slots subtract the number of dashes equals the number of crosses. So in general, n minus 1 minus k crosses. Let's think about drawing the crosses first, but we can't just do this haphazardly. For example, if I put crosses down like this, that means I have to place my 3 dashes like this. But this results in a triple smushed forbidden pair, so the forbidden pairs are only spread into 1 part, and that isn't what we want. We want them to be split into 2 parts. Similarly, I can't put the crosses down like this, because then I'd be putting my dashes down like this, which is 3 distinct parts. And again, that's not what we want to count. We only want to count the number of options for 2 parts. So how are we going to take this into account? Well, the crosses have to go down somewhere, so let's just put 2 crosses down. Once our 2 crosses are down, we've created 3 cells. How many cells is that in general? Well, there is 1 more cell than the number of crosses. So it's the number of crosses plus 1. If we add 1 to this expression here, we just get n minus k. And why have we done it like this? Well, now realize we want the dashes to fill up the cells, but we can't just do it haphazardly. If, for example, we put all 3 dashes into this cell, we'd end up with this smushed case that we had before, and we don't want that. And similarly, we can't just spread the 3 dashes among all 3 cells, otherwise we end up with this case, which is 3 parts. So you realize we need to spread the dashes out into exactly 2 of the cells. No more, no less. So let's choose 2 of the 3 cells. The 2 that we've chosen, I'm going to call bins, because they're the ones that we're actually going to be putting the dashes into. And again, how many are there in general? Well, this comes down to the number of parts we want the dashes to be spread into. And since we want r parts, we want to create r bins. And this step here, how many ways are there of actually making that selection of 2 bins? Well, we had 3 cells, and we needed to choose exactly 2 of them. So 3 choose 2 ways of choosing the bins. And what is that in general? Well, we have n minus k cells, and we need to choose r bins. So that's n minus k choose r. So to recap, we've got 2 bins, and we want to place our 3 dashes into those 2 bins. And we want to make sure that no bin is empty, because if all 3 dashes go into one bin, then that represents a possibility where all the forbidden pairs are in one part, but we necessarily need 2 parts. So how many ways are there of spreading these 3 dashes into 2 bins such that no bin is empty? Hey, wait a minute, this is stars and bars. We already know how to do this. I bet you were worried this was never going to come back. So we know if we've got n objects into k bins such that no bin is empty, it's n-1 choose k-1. Objects -1 choose bins -1. So we've got 3 objects spread into 2 bins such that no bin is empty. This is 3-1 choose 2-1. And what about in general? Well, it's the number of dashes, k, spread into the number of bins, r, which by stars and bars is k-1 choose r-1. So all of this culminates in the fact that we have 3 choose 2 options for how to select the bins, and then for each bin selection, we have 3-1 choose 2-1 options for how we spread the dashes into those bins. So it'll be this times this to get the total number of possibilities. And if you remember, we had 3 choose 2, which is 3, 3-1 choose 2-1, which is 2, 3 times 2 is 6, and that is exactly what we had before when we did it by hand. In the general case, we will multiply these 2 together. But also remember that each part can be ordered or reversed. So we're going to be multiplying this by 2 to the power of 2, the number of parts. So in general, we will multiply these 2 together and then multiply by 2 to the power of r. So all in all, in general, the number of ways for a permutation on n distinct objects to contain at least k forbidden pairs split into r parts is this. And we're not done with this section yet, but this is the most challenging part. To complete this step, remember that we want the number of ways to contain k forbidden pairs in total. All our formula does at the moment is say if you have k forbidden pairs but spread into r parts. So how do we gather them all together? Well, realize that no matter how the forbidden pairs are separated, they must be split into some number of parts. So we can take all the cases where the forbidden pairs are split into 1 part, all the cases where they are split into 2 parts, all the cases where they are split into 3 parts, and all the cases where they are split into k parts. We stop at k because k is the number of forbidden pairs, and you can't split them up into more than k parts because k parts represents when all the forbidden pairs are completely independent. So we just need to add up all of these cases, and we know the formula for each of these cases. So when r equals 1, we have the formula here, and we need to add that to the formula when r is equal to 2, and then we need to add that to the formula when r is equal to 3, and so on, all the way up to the formula when r is equal to k. So that is the answer that solves this problem. We take the sum of this formula from r equals 1 to k. So that formula there is actually the solution to this first problem that we had here, the number of ways to contain k forbidden pairs. And like I said, that was the most difficult step in this entire journey, so I'm really grateful that you stuck with it. Let's tackle this one next. This gives us the number of ways of containing k forbidden pairs, the number of structures or shapes, if you will. How many permutations are there for each case? And this isn't as complicated as it sounds. So we have the number of ways of arranging k forbidden pairs into a permutation on n integers. But how many permutations are there for each possibility? Let's answer that question now, and we'll start just by looking at an example. So back to our classic example of n equals 6 and k equals 3. So that's a permutation on 6 integers with 3 forbidden pairs. Let's use our formula that we've just discovered to calculate how many possibilities there are for how those forbidden pairs are arranged. So substituting n equals 6 and k equals 3 into this formula produces this. So this is the case when r equals 1, r equals 2, r equals 3, and then we just work these all out and add them all together. So there are 38 possibilities, which should sound familiar. Now, the question is, how many permutations are there for each of the 38 possibilities? So, for example, one of our 38 possibilities is the forbidden pair 1, 2, the forbidden pair 2, 3, and the forbidden pair 6, 5, where 1, 2, and 2, 3 are smushed together. This is just one of our 38 possibilities, but the question is, how many permutations can you write that contain 1, 2, 3, and 6, 5 somewhere inside of it? So for example, the permutation 4, 1, 2, 3, 6, 5 is an example of a permutation that contains both of these structures of forbidden pairs. Another one might be 6, 5, 4, 1, 2, 3. How many permutations are there in total, and how many are there in the general case? Well, think of the list of integers from 1 to 6, or in general, from 1 to n. Now, every time we force a forbidden pair on this list, we glue two of the numbers together. So here, for example, 6 and 5 are stuck together. Any permutation we write in this example has to have 6 and 5 concatenated. They are stuck together. Similarly with 1, 2, and 3. Now, what we realize is that every forbidden pair that we include glues two numbers together. So if we start with n numbers, or in other words, n objects, whenever we include a forbidden pair, we now lose one of the objects. So there are now n-1 objects. If we include another forbidden pair, and it doesn't matter where that forbidden pair is, whether we are extending a forbidden pair in a smushed case, or another forbidden pair out here that's independent, we always reduce the number of objects by 1. So now our objects look like this. We've got one big object there, one object there, one object there, and all the way up to n. So, including a forbidden pair reduces the number of objects by 1. Once we've included k forbidden pairs, we have n-k objects. You could see this in our specific example here. The string 1, 2, 3 has to appear as an entire unit, as does the string 6, 5. And we also had 4, which is its own unit. So there are basically 3 objects that we can shuffle around because we can't unstick those numbers. So the number of ways of arranging those 3 units is just 3 factorial, or in general, n-k factorial. And remember, this is true for each of our 38 possibilities. So each of the 38 options for how the forbidden pairs are structured has 3 factorial permutations associated with it. Or in general, this giant formula here, which produces the number of possibilities, needs to be multiplied by n-k factorial, because that's the number of actual permutations for each possibility. And that addresses this next problem here. So we have the number of ways to contain at least k forbidden pairs. Now, as for the number of permutations with at least k forbidden pairs, we take this formula here and we multiply it by n-k factorial. We are just one step away from solving this problem. Now, remember when I said not to worry about the fact that we are counting each permutation multiple times because we're actually counting the number of permutations that contain at least k forbidden pairs? Well, now is when we worry about it. So earlier, for example, I had the case 1, 2, 3, 4 as an example of 2 forbidden pairs split into 2 parts. So every permutation with the structure 1, 2, 3, 4 gets counted in that case. But those permutations will also be counted again because 1, 2, 2, 3, 3, 4 is an example of 3 forbidden pairs split into 1 part. So that permutation is going to get counted again. So all of the permutations are being counted multiple times in multiple ways. So how do we untangle all of that to get just the plain old number of ways of having a permutation containing any number of forbidden pairs? Well, this is where we appeal to the Inclusion-Exclusion Principle. And it's quite a complicated process, so it's going to be easier to understand if we appeal to a very specific example. So take a look at this example we had just a moment ago, 6, 5, 4, 1, 2, 3. This contains 4 forbidden pairs in total, 6, 5, 5, 4, 1, 2, and 2, 3. I want to know how many times it gets counted in this formula as we vary k. Because what this formula does is it counts the number of permutations that contain at least k forbidden pairs, but it overcounts them in some way. So for example, when k equals 0, this is going to count the number of permutations that contain at least 0 forbidden pairs. And in fact, if you substitute k equals 0 into here, this whole thing just becomes n factorial. So it's going to get counted once there. But when k equals 1, this formula counts the number of permutations that contain at least one forbidden pair, and it counts them once per forbidden pair that they contain. Because remember, when we constructed this formula, we considered the 6-5 case and counted all of the permutations, then we considered the 5-4 case, then counted all of the permutations, and so on. So for each single forbidden pair it contains, it's going to get counted. So in fact, when k equals 1, this thing is going to be counted 4 times. Now, when k equals 2, it's going to be counted when we consider the 6-5-5-4 case, it's going to get counted in the 6-5-1-2 case, and so on. And if you add up all of the possibilities, what you actually get is that it will be counted 6 times. In the k equals 3 case, it will be counted in the 6-5-5-4-1-2 case, it will be counted in the 6-5-5-4-2-3 case, and so on. And again, if you work that one out, it will be counted 4 times. Finally, in the k equals 4 case, it's only going to be counted once, because it will only be counted in the specific case 6-5-5-4-1-2-2-3. So it will only be counted once there. And obviously it isn't going to be counted at all in the k equals 5 case, because that counts the number of permutations that contain at least 5 forbidden pairs, and this only has 4, so it actually doesn't get counted there at all. Here's the step that's going to blow your mind. We're going to do our inclusion-exclusion routine now. So when k equals 0, we want to include all of the permutations, because we start with all of them and we hope to delete all the ones that contain forbidden pairs. So then we delete all the ones that contain at least one forbidden pair. But that over deletes, so then we include the k equals 2 case, we exclude the k equals 3 case, include, exclude, and so on. Let's see exactly how many times this specific permutation gets counted, because we want to count it exactly 0 times, because we want to delete all of the forbidden pairs that contain any number of permutations. So the ones that we'll be left with are the ones that we include at the start, but then they don't get excluded at all. So the ones that we'll be left with are the ones that contain no forbidden pairs. Let's see how many times this specific permutation gets counted. So we include it at the start, so at the moment it's been counted 1 times, and then we exclude it in the next step, so we subtract 4, and at this point it's been counted -3 times, and then we re-include it at the next step, so we add 6, so that brings our total count up to 3, and then we exclude it, so we delete 4 copies, and that brings our count down to -1, and then we include again, which brings our total count to 0, and then we subtract 0, but that doesn't change the total count. You can see that this permutation has been counted exactly 0 times. It's so good. Now, how can we ensure that these numbers always conspire to make 0 when we've got any number of forbidden pairs? And you've probably recognized these numbers 1, 4, 6, 4, 1, but let's show why they are produced. Well, if you think about it, if this permutation contains 4 forbidden pairs, how many times will it get counted in the k equals 1 case? Well, there's 4 forbidden pairs, and we want to select one of them, so it's going to be counted 4 choose 1 times. Similarly, when k equals 2, how many ways are there of selecting 2 of these forbidden pairs when there's 4 in total? That's 4 choose 2. And that pattern is going to continue for all of these cases. So let's just fill those in. And that's even true down here as well, where we have 4 choose 5. It's impossible to choose 5 objects from a pool of 4, so we get 0. And it's also true up here, because here when k equals 0, we have 4 forbidden pairs to choose from, and we want to select none of them, so we get 1. And this example was arbitrary, which means this number of forbidden pairs here is arbitrary, so I could replace this 4 with anything, and all of these blue 4s would get replaced, but always you can see it's going to print out a row of Pascal's triangle, and since we take the alternating sum, what do we know about the alternating sums of rows of Pascal's triangle? It's always 0! Oh, it's just so good! So just to reiterate, if this permutation contains any number of forbidden pairs, it's going to be deleted as part of our inclusion-exclusion routine. The only ones which will be left are the permutations that contain no forbidden pairs, and they are exactly the ones that we want to count. So to finally complete our formula, realize that we need to sum this formula up as we vary k, but we need to take an alternating sum. So remember that example I just had? I added the k equals 0 case, I subtracted the k equals 1 case, and then I added the k equals 2 case, and so on. So we have the sum as k varies from k equals 0 up to n minus 1. We start with k equals 0 because we start by including all of the ones that contain at least 0 forbidden pairs, i.e. all of them, and we stop at n minus 1 because if we've got a permutation on n objects, the maximum number of forbidden pairs it could possibly contain is n minus 1. And remember, we want to make this an alternating sum, so all we do is we stick a minus 1 to the power of k here, and that will be plus 1 when k is even, and minus 1 when k is odd, so it'll produce an alternating sum. Phew, what an epic process. And I bet you're wondering how I feel now that I finally have the solution to the problem that I've been obsessed with since my childhood. Well, I've got to be honest. I hate it. Look at that, it's horrible. I really thought this problem would have a nice, elegant answer, but this is a formula only its mother could love. Now actually, there is a tidier version of this. Check this out. Here I'm going to construct something that's a bit like Pascal's triangle, but I'm going to construct the entries in a different way. So we start with this, and then to construct the next entry, you add the two entries directly above it, and the one vertically above it. So 2 plus 1 equals 4. And again, imagine that we're in a kind of sea of zeros, so this one would be 2 plus 0 is 2. And similarly over here for 1. And then for the next row, we have 2 plus 4 plus this vertical one gives us 8, and so on, you get the idea. And now I'm going to make what we call the signed version of the triangle, which is where we make the entries positive and negative based on these diagonals. So it'll be positive, negative, and so on. So what on earth am I doing? Well, here's the punchline. If I choose a specific row, and then take k factorial multiplied by the kth entry, and do that for all the entries in a row and add them all up, let's have a look at what we get. And I should clarify here that unlike Pascal's triangle, we actually start counting from 1. We don't start counting from 0. So this is the first entry, the second entry, and so on. Sorry to all the computer scientists. So for the n equals 4 case, we do 1 factorial times the first entry, plus 2 factorial times the second entry, plus 3 factorial times the third entry, and so on, and let's have a look at what we get. So it turns out to be 2. Big deal. Let's look at the next one. We get 14, and so what? But let's look at the next one. And if you do it for n equals 6, you get 90. 2, 14, 90, oh my god, it's those numbers again. And yes, it's true, this triangle somehow yields the solutions to my original finger game. Where did this triangle come from? Because it's like a weird alternate version of Pascal's triangle. Well, I discovered this on the OAIS because it was conjectured that this triangle would also be an alternate way to produce these solutions, and I managed to prove it. Moreover, the research papers that I used to help me derive this formula actually went about things differently, developing some much more general theory, a specific case of which is used to solve Hertzsprung's problem. All of this is great stuff, but this video is already far too long. So if you want to hear my discussion of those research papers, as well as see my proof of how this triangle is connected, you can find them in an extended cut of this video available to my Patreon supporters. As well as that, my patrons now get early access to my videos, they chat to me in our dedicated Discord server, they get to see behind the scenes updates, and they get to see some silly bloopers. And if the producers really want to chest their champions, that is what I just said. Well done, Alex, you cannot talk. Well, Holmes himself said that yep, that's what Holmes said. He said If any of that interests you, or if you just want to support the channel, please consider supporting me on Patreon. I'd really appreciate it. And I just want to make something very clear about those extended cuts. The main story of each video, the main content, will always be freely available, and I believe very strongly in that. The extended cut is just there for those additional tangents and footnotes that I can't squeeze in to the main video for the sake of pacing. It's like Lord of the Rings. You know, the theatrical cut, that's the complete story, and the extended cut is just there for people who want the extra bits. Even if the final answer is kind of ugly, I loved the process of working through all of those steps to derive this solution. I guess the only thing left is to celebrate the only way that I know how. Cheers. Thank you so much for watching. Don't go anywhere yet. I've got a very special announcement. Longtime viewers of the channel will know that last year I did a 24-hour charity live stream where I raised money for Refuge, a UK charity supporting women and children victims of domestic violence. Since I'm terrible at running actual marathons, I decided to do a maths marathon, where I completed 24 maths exams in 24 hours. I'm going to be doing the same thing this year, except I'll be raising money for Mind, a UK charity that supports people with mental health issues. It's a topic that I'm really passionate about, so please support me if you can. I haven't finalised any of the details yet, so make sure you subscribe and look out for updates because it is going to be in the next couple of months or so. Thanks again to my Patreon supporters who keep the channel alive. If the benefits I mentioned earlier interest you, or if you just want to support me, please consider signing up using the link below. This has been another Proof Under Another Roof, and remember, this is a problem I've been obsessed with since my childhood that I solved by working alone in secret. All I'm saying is, I'm basically Andrew Wiles. If only.